All right, this is the 10-4, roger that, over and out video using inscribed angles and polygons. Okay, so quick little vocab section. The inscribed angle is just an angle whose vertex is on the circle itself. The arc that is opposite the inscribed angle, if we continued with the rays, is called the intercepted arc. Right over there. So those are the two vocab words that are going to be used in these theorems. Right, there are 4 theorems, but really 3 of them, actually all 4 of them, are very, very, very much related to each other. They're really results of one another. And they're actually all really results of a powerful 10.5 theorem that we'll talk about next week. Yeah. Lots of powerful theorems, and they're all very interrelated. Anyhow, that's coming up soon. All right, so the first is that an inscribed angle is exactly half the measure of the intercepted arc. Singular. So this angle here at D, just call it theta here, measure of angle ADB, that angle right there, it's actually half of the opposite arc, the intercepted arc. So that's cool. Because of that theorem, actually leads right into this theorem. When you have 2 different inscribed angles that have the same intercepted arc, because of a result of the previous theorem, these 2 angles must be congruent. So when 2 inscribed angles have the same intercepted arc, then the 2 angles are congruent, and it's really a result of that last theorem we just talked about. Additionally, let's look at inscribed angle C here for a second. The intercepted arc of a 90-degree angle should be 180 degrees based on the first theorem, and that's going to mean if that's 180 degrees that AB is actually a diameter. So when you have a right angle as a inscribed angle, the chord that you can draw between the 2 terminal points of that angle is actually a diameter. So that's going to be really cool. Whenever we have a right triangle, we get to use our awesome friend, the Pythagorean theorem. So that'll all be fun. And one last theorem from this section, and then we'll take a look at these happy examples. When we have an inscribed quadrilateral, the opposite angles are supplements. And this is actually based on the previous theorems, if you think about it. Get a couple different colors going on here. So if I take a look here, angle D, for example, and then angle B, which are opposite angles, the sum of their intercepted arcs are 360. So that means these 2 angles must add together to be 180. I don't know what these angles are, but I know that the opposite angles must be supplements, because two opposite angles here in an inscribed quadrilateral, their intercepted arcs are the entire circle, 360 degrees. So the sum of the two arcs are 360. That means the sum of the two angles are half of that, 180. So really, really cool stuff going on here. Lots of really interesting connections that we can make from these couple of theorems. All right, let's do a couple examples. Again, my mental math isn't really firing on all cylinders, so we'll have the old calculator here ready to go. With each one of these examples, I'm going to mark the picture up. I don't know what's going on here, so let's just take our time with it and add in all the information that we can deduce, and let's see what we can figure out. All right, first thing I notice here is I have a 50-degree angle right here. That means this intercepted arc is going to be twice that inscribed angle. So I can figure that part out already. Using that same theorem in reverse, if this intercepted arc is 48 degrees, that means the inscribed angle is going to be half of that. All right, so we know that. All right, so let's see here. The measure of angle BDE, oh, we just figured that out. That's 24 degrees. All right. And let's see, the measure of arc AB. Don't actually think we can figure that one out. Why did I ask that? I think I need a little more information. I think I've deduced everything I can. Except, well, so this is going to be cheating here a little bit. What I'm really going to know about that is that it really should equal 360 minus these other ones. So it's definitely cheating a little bit because I'm not actually answering this question for sure, but I'll say what I can figure out about it. So it's got to be equal to 360 degrees minus 100 degrees minus 48 degrees minus the measure of the one that I don't know, DE. You know what? I'm going to take this as a learning opportunity, even though I goofed up writing this example a little bit. It's important to know what we cannot conclude. It certainly looks like maybe these two arcs are the same, but I don't want to conclude that unless I saw some congruence marks. So I can't actually write a final answer here in terms of a number, but I can simplify this expression down a little bit. So the measure of this arc is exactly equal to 210 minus BE. DE. What am I thinking? My picture is very much not drawn to scale. Probably because it's very much not drawn to scale. Yeah, this is a horribly drawn picture in terms of its scale. But we'll just trust in the numbers, and yeah, because they all have to add up to 360. So the measure of this arc must be 360 minus that, minus that, minus that. So 360 minus all of that. It's going to be the measure of DE. I'm going to cross that one out because, again, it's going to be a similar story to that. Let's just figure out what we can. The measure of arc AD is 100 degrees. All right, that's what I should have just done, these two. Let's forget about this guy. I don't think there are any problems on the homework like that, not without more information. If I had some congruent marks here or here, then I could actually figure out those other things. Maybe I forgot to put those in. Whatever. I looked at the example problems. Those are good enough. Apologies for asking a little bit more than we could actually solve for. All right, moving on. Let's see. Okay, well, let's see what can we do here. Okay, so that has to be twice the inscribed angle. So we know that is 62 degrees. And measure of angle ACB, that's from A to C to B, this guy right here. Ooh, hey, wait a minute. That has the same intercepted arc. So these two angles must be congruent because this angle is equal to half its intercepted arc, which is a theorem that we have. Sweet. All right. So that's all fun. Next example. We have a diameter. Sorry, move some stuff out of the way. We have a diameter here because it goes through the center of the circle. We can deduce using the original theorem. That means this is 180 degrees. That means the inscribed angle is half of that. So it must be a right angle there. And that is the answer to the question. Sweet. And finally, I hope I wasn't too ambitious with this last problem and made a similar mistake about asking too much. No, I don't think so. I think we got this. This one is definitely the most challenging one of them all, but let's first figure out probably the easiest part. So all four of these arcs must add up to 360. So let's subtract the 3 we know to get the one we don't know. And then we'll kind of go from there. So this must be a 66-degree arc over here. All right, what else do we know? A couple of things. So first off, let's maybe solve for A first. All right. So I'm going to solve for A. We can take a look at the intercepted arc. And if we add these two guys together, I think that's 120 degrees. Just using the arc addition postulate. And if that adds up to 120 degrees, this 3A must be half that. And there's a lovely equation to get A equals 20. Yeah, because this guy must be a 60-degree angle. It's half of the intercepted arc. Well, that can give me D straight away, because the other half of the intercepted arc is the rest, 240. So half of 240 is 120. No, that's a lie. Oh, no, it's not a lie. I was confusing myself because I thought 20 and 120 should be supplements, but that's just the value of A. The angle here is 60, which is supplements with 120. Silly me. All right, we get a different color pen here to solve for these other two guys. Let's see what's going on here now. Lastly, B and C. All right, I'm going to take a roundabout way. Let's solve for C first. So looking at the intercepted arc from inscribed angle C there, we can add these two guys together. And then C must be half of that. So it looks like C is 92. 92 degrees. I'll put a little degree in there so we can just write the C is 92. But this angle is 92 degrees. And then for B, we know that these two angles, and not very drawn to scale, these two angles must be supplements. So that means this angle here must be 88 degrees. So if 4B equals 88, then B is 22. All right. Good stuff. All right. Sorry about asking a couple of things that we couldn't actually explicitly solve for in this example. But you can see sort of how this works. The key here to all of this is that the inscribed angle is exactly half of the intersected arc. That principle alone can pretty much allow you to conclude everything else. The theorems are, of course, shortcuts, but they're all intertwined. They're all based on this original theorem. And then you can kind of conclude all these other theorems based on that. So that's the key to remember here. And this is absolutely an MCAS style question. So of all the theorems, if we make it later in life and forget most of these, this is the one to remember. This is going to be the question on the final based on the Chapter 10 circle content, assuming, of course, we have a final, if hopefully this whole quarantine thing will be over soon. Oh, yeah, that's my phone. All right. Thanks a lot, kiddos. Where's my mouse? There it is.